So now let's talk about a topic that is loved by chemistry students everywhere. No, I'm just kidding. But significant figures. So let's talk about significant figures. So numbers used in chemistry can be described as being either exact or inexact. So we have two types of numbers, exact numbers and inexact numbers. An exact number results from counting objects, so counting numbers or part of a definition, an exact definition. So you can count that you have 10 fingers, you have exactly 10 toes, or there are exactly 100 centimeters in a meter. So this is an exactly defined relationship. While inexact numbers result from a measurement or observation and contain some uncertainty. So whenever we make a measurement, there's some uncertainty, which leads to the value being described as being inexact. So if you use a ruler, you have to make an estimation, use a mass balance, so the instrument estimates and it has some limitations. If you use a graduated cylinder to measure volume, that also requires some estimation and contains some uncertainty. So a container contains 71 macadamia nuts and weighs 125 grams. So even though both of these values are numbers, one of these values is exact and the other is inexact. And so the number 71 is, well, what do you think it is? So pause it, think about it. So hopefully you said it's an exact value because we can count it, so it's a quantity that we know without any uncertainty. So all data that are determined by counting are exact, and these, for exact numbers, we don't use instruments, measuring instruments or devices to obtain them. Also, exact definitions, like I mentioned, so meter to centimeters, but there are also exactly 12 inches and 1 foot. So I'll say this here because repetition deepens the impression. So metric to metric relationships or conversions are exact, as well as English to English are exact relationships. But going between the two, metric to English, are inexact. So measurements, on the other hand, such as the mass of the container of nuts, so we'd use a mass balance to get the mass in grams, for example, have a certain degree of uncertainty with them. And so there is no measurement made in which we are absolutely certain of the answer because we and our instruments are imperfect. And so the uncertainty in a measurement describes how sure we are that our measurement is correct. So that uncertainty tells us about how sure we are that our measurement is correct. So consequently, numbers obtained by measurement are always inexact. Underline that. So always inexact. Measurements are always inexact. And so this is a result of equipment errors, as well as human errors. So we and our instruments used to measure are imperfect, and our instruments have inherent limitations. And so we could use mass balances that are more sure or have more certainty, so it provides more digits, but still there's some uncertainty associated with the value. And a good thought idea I had related to this, so let's say you want to get your kitchen countertops replaced with granite, and the company will charge you $50 per square foot. Would you want the company to measure the square footage using a piece of string or a measuring tape? What this is trying to get at, or what I'm trying to get at here, is that your measuring device will determine your will determine how certain you are with the measurement. And so since you're paying for this, it's probably not likely that they'll undercharge you. If anything, they'll overestimate. So you would want them to use the measuring tape. And so whenever we measure a quantity, there is a degree of uncertainty associated with the result. And the last number, the one furthest to the right, is an estimate. And it depends on the type of measuring device we use to obtain it. And the last digit in a measure is referred to as the uncertain digit. So that's the estimated digit. And then another good example, so we would be more certain about our value or measurement using ruler B than we would ruler A, because we could only estimate one, or we should only estimate one digit using ruler A, but we can estimate an additional digit using ruler B. So measurements made with ruler A will have greater uncertainty than those made with ruler B. And so when using the ruler at the top to measure the memory card, we could estimate 2.5. We are certain about the 2, but we're not certain about the 5. So that's the uncertain digit, that's the estimate. And then the uncertainty is generally considered to be plus or minus 1 in the last digit. So 2.4 to 2.6, so somewhere in that range. When using the bottom ruler to measure the memory card, we might record 2.45. So we know it's above 2.4, but below 2.5, so it's somewhere in between. So we know for sure it's not above 2.5, so 2.4, and then we estimate the last digit. And so whenever we make a measurement, without an equipment like a mass balance. So when we use a mass balance, we should always record all the digits that it gives us. So, but when making a measurement, we always estimate one digit. So don't estimate any digits on the mass balance, so just record what it gives you. But if you're making a measurement with a ruler, for example, you always estimate one digit. So then we would say, well, see what you would measure the length of this paperclip as. So pause the video, measure it, then come back. So for this one, you know for sure it's 2, and then you estimate one digit. So you would say about 2.3 centimeters. And then this one, you would say 2.3, and then estimate an additional digit, 3.32 centimeters, but you might have recorded a slightly different measurement. And so that's where the uncertainty comes in. And so significant digits or significant figures are all the digits in a measured value, including one estimated digit. So this one would have 3 significant figures, so all the values including one estimated digit, and this one would have 3 significant figures. And so if we did a similar process, so this one would have 2 sig figs using this ruler, and then this one would have, so sig figs for short, because nobody wants to say significant figures all the time, but sig figs. So if you see that, that's what that stands for sig figs. So then this would have 3 sig figs. So let's talk about the rules for determining the number of significant figures or sig figs in a measurement. So in any measurement, all non-zero digits are significant. So all values that are not 0 are significant. So this one would have 3, and we start counting with the first non-zero digit. So this one would have 3. This one would have 1, 2, 3, 4, 5, 6. So 3 significant figures, and then 6 significant figures. And then zeros, they may or may not be significant. Because zeros can be used either as part of the measurement or merely to locate the decimal, they may or may not be significant. And so zeros are significant when they occur between non-zero digits, so they're sandwiched in between. So we start counting with the first non-zero digit, and so then if they're sandwiched in between, they get counted. So 4 sig figs, and this one has 1, 2, 3, 4, 5 sig figs. And then they are also significant if they occur at the end of a number that contains a decimal. So the decimal is explicitly shown. So 1, 2, 3, 4, 5. So that decimal is there. So those are significant, as well as this one. So since the decimal is shown here, we interpret this as 3 sig figs. Zeros are never significant if they occur at the beginning of a number. So again, start counting with the first non-zero digit. So 1, 2, 3. And then this one has just 1. And then a problem arises when a number ends with a 0, or ends with zeros, but contains no decimal point. So there's some ambiguity as to whether we intend for that 0 to be significant or not. So these are called trailing zeros. So trailing zeros come at the end of a number, and so we interpret them. The rule is we interpret them as not being significant. If your decimal is not shown, that is not significant 0. So 3 sig figs, and then this one has 1, 2, 3, 4, 5 sig figs. And so to eliminate this ambiguity, so it's best to express such numbers using scientific notation. So hopefully you watched that video on expressing numbers in scientific notation. So if we, let's say we had the object had a mass of 10,300 grams, so question mark, are these not significant? So to convey clearly to 3 sig figs, so 1.03 times 10 to the 4th, to 4 sig figs, 1.030 times 10 to the 4th, and then 1.0300 times 10 to the 4th would be 5 significant figures. So to summarize, so leading zeros are never significant. Trapped zeros or sandwich zeros are always significant. Trailing zeros are only significant when behind both a decimal and a non-zero value. Okay, and then the next thing that students love is we're going to look at how many significant figures we should report when we make calculations involving measurements or numbers. So when multiplying or dividing two numbers, the answer has the same number of significant figures as the original number with the least number of significant figures. So the rules differ for multiplication and division versus addition and subtraction. So that's important. So we want to look at the original value or measurement with the least number of significant figures. So this one has how many? 4. This one has 2. And so even though you may plug this into your calculator, and last time let's see, divided by, yeah, so you would get this value, but you would not write this as your final answer. So how many sig figs should we report our final answer to? So since this had 2 and this had 4, we should report only to 2 sig figs. So we look at this one, and then we look next door. If this is 5 or more, we round up. If not, keep it the same. So we would say 64 miles per hour. Okay, and so then answer 64 miles, and remember units are important. And then, okay, that's there it went. So Slide was out of order. So yeah, so the rules, so if it's between 0 and 4, don't round it up. If it's 5 or more, you go next door. That is, you round it up. So 64 miles per hour. And then this one, so when we multiply, look at least number of sig figs, so 3 versus 4. Our answer should have 3 sig figs. And then when you divide, again, 3 versus 4, so we want 3 sig figs. Okay, rounding off values, yes. And then when adding or subtracting, the rules change. Okay, so seat belts. When adding or subtracting, the answer, so the sum or difference, has the same number of decimal places as the original value with the least number of decimal places. So now we're looking at decimal places. 10.11 minus 3.6. So this has 2 decimal places. This has 1. So our answer should just have 1 decimal place. So 6.5. And so then, if actually how many significant figures that contain, then you should say 2. But 1 decimal place or 2 sig figs. And so then subtracting, so then we have 2 versus 4. So this is the last one that we keep, but we round it up to 3.24. Okay, so 4.1 grams plus 7.08 grams. So what would be the correct value to report? So pause the video, think about it, come back. So we are adding, so we want to look at the least number of decimal places. So 1 versus 2, so our answer should have just 1. So our answer should be C. Now multiplication, so pause the video, come back, or work through it, come back. So now we're looking at significant figures. So this has 2, this is 3. We want a value with, or to report just 2 sig figs, so the least number of significant figures as our original value. And then an interesting example, so let's say we had 100, so remember these trailing zeros are not significant. So this is the last significant digit, and let's say we're adding it to this. So then this is the last digit that should be significant. So we would round our answer to 5,400, or we would say express it in scientific notation, 5.4 times 10 to the third. So this type of example doesn't come up too often, but I thought it was interesting enough to point out. So we look at the last significant digit in the value and match our answer to have that amount of significant digits. And then let's say we had order of operations involved. So please excuse Pandas, please excuse my dear Aunt Sally. So then since this is in parentheses, so we do that first, and so then we think about the rule for subtraction. So then that should have just 2 sig figs, but try not, so keep extra digits so you don't introduce rounding errors, so don't round off just yet, but maybe put like a little line above it so that you remember that that should just be the last digit you retain. And then you want to multiply that, so 3.92 essentially, but keep that into your calculator. So multiply that value by this value times this value, and so then our final answer should have just 3 significant figures, since technically this one we kept at 3 significant figures based on the subtraction step. So our final answer should have 3 significant figures. Okay, so your turn. Report the answers to the correct number of significant figures. So pause the video, work through these problems, come back. Okay, so let's do this first one. So here we're multiplying. The rule is the least number of significant figures. And I'll show you this. So in terms of units, 84.5 gallons, and then I can write this as 3.1 miles per gallon. And so gallons cancel out, and I'll be left with units of miles. But if I plug this into my calculator, I get about 261, I believe. Let's see. Yeah, 261.95. So here this has 2 sig figs, this has 3. So I want 2 sig figs, so this is the last value that I retain. So I look to the right of it, and so since it's I'm gonna drop this, but I don't round it up, I keep it the same, so 260 miles. So this is to 2 significant figures, so this value rounded to 2 significant figures. And then the next one, so I add, so I'm looking at least number of decimal places, and so then I just want 1 decimal place, so 120.3 gallons. Dividing, look at least number of significant figures. So this has 2, this has 3. So I want my final answer to have just 2. And remember, this is not significant. So numbers are zeros at the start are not significant. Start counting here. So units of grams per milliliter. And then I have order of operations to consider. So I subtract first, so that gives me 9.5 meters, and then divided by 2.74 seconds. So subtraction, least number of decimal places, so 1, and then divide least number of significant figures. So then my answer should be 3.5 meters per second. And then, so those are all measurements, so values or measurements, calculations involving measurements, but we may have a exact value involved in our calculations. And so like if we took the average, for example, then we divide by an exact number, so average, and I have an example, average height of plants. So let's say we had 3 plants, then I would divide by 3, that's an exact number. So it turns out that we don't consider exact values when determining the number of significant figures to report in our value, or our final value, or final calculation. So when making calculations, exact numbers are ignored when determining the number of significant figures in the final result. And we said that the exact numbers were counting numbers, or those from exact definitions. So metric to metric and English to English. Exact numbers are considered to have an infinite number of significant figures, and so then that means a lot. So we're going to ignore those because we're usually looking for the least. So you measure the height of 3 plants to be the following: 30.1, 25.2, 31.3. Calculate the average height of the plants. So what we'd have to do is add them up, then divide by 3. So, but we ignore the 3. So 30.1 plus 25.2 plus 31.3. And from memory, I think it's 86.6, but let me just double check. 25.2 plus 31.3. Yep, 86.6. And so centimeters divided by 3. So my answer should have 3 sig figs, not just 1. So 28.9 cm was the average.